Good evening and thank you for joining me. Today is Sunday, August 18th, 2019, and we have some stuff to talk about. We had some pretty intense thunderstorms that came into New York City today. Most notably, just west of the city, there was reports of some quarter-sized hail and some pretty damaging winds. Tomorrow, there's going to be some more thunderstorms. In fact, there's a chance of some pretty strong and even severe storms tomorrow. In fact, the NAM is showing that there's going to be some pretty intense activity. I'll show you right now what I'm talking about. So I'm going to be looking at the wrap right now because when I checked the HRRR for the 18Z run, it showed some pretty intense activity for tomorrow. There we go. Yep, looks like we're going to have some pretty strong storms tomorrow. Chance of some strong and severe storms. In fact, we're under a heat advisory for tomorrow as well, with temperatures expected to soar into the upper 80s to low 90s. Or I think that might have been for today. So the strongest chance of severe storms is going to be just west of the city. So this is what's really going to happen tomorrow. Well, what's likely going to happen. There we go. Those are the, you see those cores there? There's going to be a chance of some hailers tomorrow. And also there's going to be a southerly wind fetch here in the city. So that could increase some vorticity here in the city, which could lead to some tornadic activity. Well, not tornadic, but some supercells, especially as you get closer to the coast. So it won't be impossible, but there will be some chance of some pretty intense thunderstorms for tomorrow. And this is looking at simulated echo tops. Some tops around 50,000 feet. And looking at the current run of the NAM, of the HRRR, it's showing hardly anything. Look at that. Well, that's hour 17, so there's definitely a chance of some storms tomorrow. And looking at the next several days, next few hours, well, several hours. This is looking at tomorrow afternoon. Looking at tomorrow afternoon, scattered showers and storms, and that basically that upper level lows here. Looking at the switch gears right now, and I'm going to look right now at the European model. the European is hinting at something developing, but the thing is, model's hinting that it's gonna go out to sea, while the Canadian basically doesn't have anything at all. In fact, it has one big area of high pressure, keeping everything under control. That's weird. Look at that. Disturbances are actually moving towards the northwest. So way north of where they're supposed to. And these storms would kick off Saharan dust. So basically, the track of these storms, it's actually pushing them further north and west. I don't know if the GFS is showing that, but that's definitely a little bit odd, I have to say. See all that precipitation? See, it shows the whole Sahara is having some levels of precipitation, which is very unusual. I mean, look at that. That's showing the Sahara having storms. Look at that. And that is what kicks up the dust. It's those thunderstorms rolling off of Africa. Look at that. That's showing several inches of rain there. Isn't that crazy? Look how moist the Sahara is. This is showing several inches of rain in the Sahara. That's almost unheard of. Oh, look at that. The GFS is hinting at something potentially developing. Look at that. When you look at that, the problem is you have too much dry air. While conditions are more favorable, as in ocean temperatures and wind shear, the problem is you have way too much dry air. There's just too much dry air. And because of that, this system won't really become anything. I mean, look at that. It doesn't merge with this, and it moves off the coast, and it looks like Baja California might get quite a storm. There will be a tropical storm, potentially a hurricane, that will go up Baja Peninsula, just up the coast. So as you can see, finally all loaded. Look at this. I mean, check this out. Oh my God. This is incredible. California is going to get slammed. Yeah, I mean, this is... Let's see the Pacific. Invest 95E. Yep, that's the one. Invest 95E. That's the one we gotta watch. This is the one that's going to turn northwest, right, and north, and then right into the Baja Peninsula. There it is, right here. Invest 95E. It's gonna turn, north right into the Baja California Peninsula. Baja California. Southern Baja California South. Sud Baja California Sud. South Baja California. Right here. Baja California Sur, which means south. And it's going to come very close to Cabo San Lucas. If the hurricane can go up, if it ends up going like that, you could get a strong tropical storm, maybe even a minimal hurricane making landfall here. That would spell disaster for California with flooding, rain, and strong winds. And it looks like Phoenix is getting some storms right now. Yeah, look at that. Phoenix is getting some storms. Let's go to lightning maps right now. I'll show you, I'll see if there's any storms in the Phoenix area right now. And it looks like there are some storms. I just don't know if it's in the Phoenix area. It looks like it's northern Arizona. So there's New Mexico. Nope. Phoenix is in fact in the clear. There's no storms at all in the Phoenix area. Let's look at Phoenix and Mesa radar right now. And in fact, it's clear. It's entirely clear for the Phoenix area. So, yep, Baja California better watch out. Looks like pretty healthy storms coming there. And let's look at the ensembles right now. And look at the GFS ensembles. It's like something actually may end up happening. Look at that, right? Ensemble precipitation accumulation. Looks like something may end up happening. It may just be a cluster of thunderstorms, but something may develop. The remnants are off this one. Look at that. Remnants are off the California coast here. So. Number 20. Looks like not. See, as soon as it enters the Gulf of California, look at that, it re-strengthens right here. That's a concern, because right here, look, it makes landfall as a hurricane in Baja California Sur. You have a hurricane coming ashore. Now it's a tropical storm. Goes off the coast, weekends. Yeah, that's 5,000 feet at 850 millibars, 37 degrees Celsius. That's actually 98.6 degrees. Unbelievable. Yep, there's going to be a heat wave coming in. Wow, check this out. 42 degrees Celsius. Incredible. That's like 107 degrees. Incredible at 2,000 feet. And translate that into air temperatures. 35 degrees. And I guess what's going to happen? Under 4 degrees. Wow, in Virginia. Incredible heat. An early September heat wave in New York. Incredible. Look at these water temperatures here. Just incredible. Okay, it's not too incredible here, but it's warm. Look at that. Extremely warm water temperatures. And one more thing is earthquakes. Yep, earthquakes. In fact, there's a pretty... the swarm is continuing with the 3.6 today. Wow. And that was actually past hour, so 3.6 in the past hour, so quakes are continuing. In fact, there was a good sized swarm at Coastal Junction today, so this earthquake swarm is definitely not subsiding at all. In fact, it's getting very close. It's actually getting closer and closer towards the Greylock Fault. There already has been some quakes along the Greylock. You're at 3.6 about an hour ago here. 3.3, 3.6, and a depth of 8 kilometers. So quakes are continuing. Also, you're having quakes in Long Valley caldera. Look at that. You had a 0.8, a 1.6, a 0.3, 1.4, 1.5, and 1.3, and a 0.6. And looking at 7 days all magnitude, there is still some swarming going on in Long Valley, with a 1.5 that occurred on the 12th, which is 6 days ago. And a fairly good sized swarm is continuing here with a 2.1 occurred yesterday, I believe. Yep, 17th, yesterday. There was a 2.1 at a depth of 5.2 kilometers. Looking at 7 days, magnitude 2.5 plus, nothing much is going on, except that massive earthquake swarm that is continuing at Coastal Junction. 3.9 actually occurred, so pretty sizable activity at depth of 2.3 kilometers. This is actually in the volcanic field itself. This is near the lava. This is near the magma chamber, so that's not good. This, of course, is not part of a magma chamber. These swarms are part of a magma chamber here. Go back to 7 days all magnitude. So I'm going to 7 days all magnitude. This is these faults are actually the periphery of the caldera boundary. The caldera boundary basically go around here. The resurgent dome is actually here. So looking at terrain right now. So this is the resurgent dome. So right here is the caldera boundary. So these quakes are right inside the caldera. In fact, this is actually the resurgent dome here. There have been some quakes on the resurgent dome at a depth of about 4.5 kilometers, and that is about where the magma chamber actually lies. That is where the magma chamber is, right about here. Magma chamber is around here, and there is enough magma at Long Valley to produce a catastrophic eruption. 240 cubic kilometers of magma was just discovered. 240 cubic kilometers of magma is enough for a VEI 7. So one of the largest supervolcanoes in the world sits underneath California. Lying dormant for the past 100,000 years, now researchers have gotten a clearer glimpse into what lies below the Long Valley supervolcano, covering 240 miles of magma sitting beneath California. And it's important by saying this absolutely doesn't mean there is any imminent danger. Experts at the United States Geological Survey are actively monitoring the supervolcano, and while there has been an uptick in activity over the past 4 decades, there are no signs of an eruption. Well, what is the Long Valley supervolcano? Well, you may have heard quite a bit about the volcano sitting beneath Yellowstone National Park. You may be unfamiliar with another major supervolcano in the United States, the Long Valley caldera. The Long Valley caldera sits in eastern California, adjacent to Mammoth Mountain, which is actually a volcano as well. It's actually a lava dome, and measures 20 miles long by 11 miles wide. A caldera is basically a depression formed after the eruption of magma to the surface. As magma fills up the chamber below, the volcano expands the crust and the volcano grows. After an eruption, there is a tremendous amount of volume that has suddenly been displaced, which causes the ground above to sink into a bowl-shaped depression, which we call a caldera. And that's basically the hot creek, Yep, that's basically those are some very hot waters heated by the underground magma. The Long Valley caldera is a depression formed from the supervolcanic eruption 760,000 years ago, which ejected hot ash, lava, and toxic gases. The eruption 760,000 years ago erupted 140 cubic miles of material from the supervolcano. That's about the same level of Tambora. So it's technically not a supervolcanic eruption. Or if you consider this to be a supervolcano, then you could consider Tambora, Krakatoa, and Crater Lake in Oregon to all be supervolcanoes. Even though those 3 are stratovolcanoes, they're actually considered supervolcanoes as well. Long Valley caldera is not a stratovolcano. It's actually a caldera. And it was not a stratovolcano beforehand either. It may have been a stratovolcano that had a catastrophic eruption. But the fact that it's such a big caldera means it was probably more than 140 cubic kilometers. There's no way that such a small eruption would produce a caldera that big. Some of them are estimating actually 1,400 cubic miles, actually, not 140. A lot of the quakes that are occurring are actually in this area here. So you see Route 395? Most of the quakes are occurring right over here. This is 395, and this is Mammoth Lakes right here. So this is inside the caldera. Just to let you know, this is inside the caldera. This could be geothermal related, but this is pretty deep. Too deep to be geothermal. Also, there are quakes inside the caldera itself, which also at 4.5 kilometers. And this is very close to, this swarm is very close to Convict Lake. And Convict Lake is right on the outer periphery of the caldera boundary. Lake Crowley is actually on the edge of the caldera boundary. It is in fact possible that this whole area can be the caldera. It could be more like this. There are in fact craters, more volcanic craters within the caldera. So there's basically one source of magma feeding all these volcanoes. So it's not like one big magma chamber. I believe it's more like several magma chambers. This was actually produced by subduction. That's why it's not moving. It's not like a fault line that the earthquakes can move along, or like a fault, or this is not a mantle plume that is stationary and the crust is moving. This is because of subduction. There's actually some fault lines running through here that are causing magma to rise towards the surface, which is why you're having volcanic activity here, including the Inyo craters, which produced Mono Lake. Mono Lake was also produced by a very massive eruption. Mono Valley, Mono Lake may have been produced by a very explosive eruption. Mono Lake is a crater lake. Mono Lake caldera is what you basically call it. See? Formed 760,000 years ago. It may have been two catastrophic eruptions. Long Valley caldera and the Mono Lake caldera. Geology. Mono Lake is part of a large volcanic complex that stretches from Mammoth Mountain to Mono Lake. Isn't that cool? Except for the Sierra Nevada immediately to the west. Mono Lake is surrounded by a volcanic landscape. The Bodie Hills to the north and the Kotrak Mountains to the east. The lake did not look much like volcanoes today, but they are remnants of an earlier volcanic era that predated the existence of Mono Lake hundreds of thousands to millions of years ago. The Mono craters, stretching to the south of Mono, erupted recently in geologic time and are some of the more obvious volcanic features at Mono Lake along the Black Point and Negat Island volcanoes. The volcanic chain stretching 10 miles north to south and topping 9,000 feet may be the youngest volcanic mountain range in North America. The last eruption in the Mono craters chain occurred less than 700 years ago at Panum Crater. Panum Crater, located just above the south shore of Mono Lake, is not a true crater. It is more accurately a plug dome volcano, where cooled lava has created a massive dome-like structure that now plugs the volcanic vent at the bottom of each crater. That's actually very dangerous, too. The entire Mono craters chain is actually a series of plug dome volcanoes that erupted into existence within the last 40,000 years. Odds are the Mono craters will erupt again. Imagine a volcano erupting 2,500 times greater than the Mount St. Helens blast of 1980. 20 miles south of present-day Mono lies the northern edge of the Long Valley caldera. 760,000 years ago, the Long Valley eruption blasted more than 150 cubic miles of earth and ash skyward, burying much of the region in hundreds of feet of volcanic debris. Ash fell as far east as Nebraska. The Earth's surface collapsed more than 1 mile deep following the eruption, forming a 2,000 square mile depression called Long Valley Caldera. Today, the Long Valley Caldera is part of a large volcanic complex that stretches from Mammoth Mountain to Mono Lake. And geologists have determined the age of Mono Lake from the Long Valley eruption. 1908, prospectors drilling for oil on Hawaii Island discovered an ash layer from the Long Valley eruption beneath hundreds of feet of lake sediment. Beyond the ash layer was more lake sediment. The unlucky prospectors did not find oil, but they inadvertently discovered the secret to Mono Lake's age. Geologists determined that Mono Lake has held water since the Long Valley eruption 760,000 years ago, and lake sediments below the ash layer hint that Mono Lake could be much older, among the oldest lakes in North America. Wow, that's really impressive. So it's not in fact a caldera, it's actually a geologic lake. Potential threat, moderate. Long Valley. Look at that, highest priority. Last volcanic center, Long Valley and Mount Shasta. Look at that Clear Lake, Inyo craters, Medicine Lake, Salton Buttes. And among the highest priority is Long Valley caldera, because that's a very dangerous volcano. Wow. Mammoth Mountain, lava domes. Let's see. Moderate threat. Most recent eruption 700 years ago. Sporadic. And let's see. High threat? Oh no. Very high. Oh. That's a very high threat. So as you can see, the 16 by 32 or 20 by 10 mile Long Valley caldera east of the Central Sierra Nevada range formed as a result of the voluminous Bishop Tuff eruption, considered a super eruption about 760,000 years ago. Resurgent doming in the central part of the caldera occurred shortly afterwards. During early resurgent doming, the caldera was filled with a large lake that left lakeshore traces on the caldera walls and resurgent dome peninsula. The lake eventually drained through the Owens River Gorge. Along the caldera's ring fault, Mammoth Knolls is the youngest eruption, about 100,000 years ago. In the topographic basin, cone 2652 in West Moat is about 33,000 years old, and dacite lavas in Northwest Moat are 40,000 to 27,000 years old. The mafic chain along the west rim is 16 to 17,000 years old. The caldera remains thermically active, with many hot springs and fumaroles, and has had significant deformation, seismicity, and other unrest in recent years. A robust geothermal system inside the caldera fuels the Casa Diablo power plant, which generates enough power for 40,000 homes. Why is it considered such a high threat? Is because of the recent unrest. In fact, right now I am going to check out some of the latest deformation using GPS coordinates. Right now I will be looking at the USGS to find out some deformation at the Long Valley caldera to see whether there's uplift or subsidence that is occurring at the volcano. So this is the Long Valley caldera right here. So this is a GPS seismic station right here. And let's see. You see subsidence as low as -6 meters or -6 centimeters. And, you know, this is meters and this is 0.06, which means this is down 6 centimeters and then up by 6. So that's a difference of 12 centimeters in only, this is about 2005, I'm going to presume, 2004, 2005, 2004. So from 05, 06 through only 14 years, it rose by 12 centimeters, which is 12% of meter. And deformation is towards the northeast. Well, actually towards the southwest. This is southwest base deformation, and it's up. So there is deformation. See, it drops from the east going west, and from the north going south. So this is the deformation towards the west to west northwest. Because this is, if the northwest, it would be right over here. So this is northwest based deformation. In fact, recently, was there any deformation? Check again. These are where all the earthquakes are occurring, and in past year, yep, there is definitely upwards deformation. There is definitely deformation. There's definitely significant GPS displacement. First, it was mostly straight. There was some subsidence, and now it's inflating again. And this is what's closest towards this is the West Lake Basin. This is a tilt meter right here. Okay, that's not working. And this is showing GPS displacement. It's showing subsidence, which is good. You know, you definitely want to see subsidence at a volcano. You do not want to see uplift. And looking here, wow, look at that. This is 10 meters down. This is significant right here. This is down 10 centimeters. So this is an increase of 15 centimeters in only 4 years. That's pretty significant. And from here, 6 centimeters in only 2 years. Pretty extensive deformation, and this is near the Norris Geyser Basin. Ready? This is showing deformation from 0. It's showing very slight uplift, but very slight. Past 30 days, nothing significant. This is eastern caldera, and let's see, 15, so 20 centimeters in 4 years. Right here, 15, so down from 16 centimeters up to about, like, this is actually 22 centimeters in only like 5 years. That's pretty significant. Let's go back to Long Valley. So this is looking back at Long Valley caldera. Let's see. This is right at KRAC. This is probably a mistake here. From here, this is down, and look, uplift is continuing. Consistent uplift. So the past 9 years, they've been uplift close to 10 centimeters of uplift. So there's definitely uplift in Long Valley caldera, and consistent uplift too, which is very bad. Let's see. Down 1 centimeter between 1 and 1.5, and right now, March to September. So not a big increase, a very slight increase. And this is on the eastern side of the caldera. Not much uplift. I mean, and this is northeast side of the park. Very slight uplift. This is the center of the caldera. And that is where some of the highest levels of uplift is occurring. Let me check this out. From down 3 centimeters up, like, so there definitely is uplift here. The uplift is definitely ongoing. And this is only 5 years. So in 5 years, there's about 6 centimeters of uplift. So that's greater than 1 centimeter every year. So if you do the math, if it's slightly greater than 1 centimeter every year, so calculator, that's going to be 1 meter every century. But sometimes during extreme episodes of unrest, you can get a century's worth of uplift in only a couple of years, which is what happened in 1980. This is just outside the caldera boundary, showing very little uplift. This is inside the caldera boundary, by the way. Yeah, this is not showing any. That's not a very good measurement. This is an MCB. This is a seismometer inside Yellowstone caldera, like Long Valley. There's some quakes ongoing there. That was oceanic microseisms right here. So uplift here has been ongoing, but very slowly. So there we go. I know there was a teleseismic signature. This is GPS displacement right inside the earthquake fault. I mean, right inside the earthquake swarm. Looking at the past several days, look at that uplift again. So from -4 centimeters in the past, I'll say 7 years, there's been about 8 to 9 centimeters of uplift, which is pretty impressive, if you ask me. That's another seismometer right here. Look at that. All those quakes. Active. Where's that teleseismic signature that I saw? I saw it in there earlier. That's probably because of the weather. This is the one I was looking for. Fact, where's the teleseismic signature? Okay. Can't seem to find that. That was the one. I think it was NCSN. It's either this one or that one. Yep, there it is. There's a pesky teleseismic signature right here. Oceanic microseisms. Well, thank you for watching. Bye.